The De Beers Consolidated Diamond Mines in South Africa have operated caves across 7 mines, more than 20 block caves across 7 of their diamond mines in South Africa. And this presentation is about some specific problems that we encountered at 2 of the mines. So at the Kalinin diamond mine, we had to change our undercut mining sequence. And at another one of the mines, we had to improve our support design. Otherwise, we just simply wouldn't have been able to function. So the Kalinin diamond mine is situated obviously in South Africa. It's about 100 kilometers away from the biggest city in South Africa, Johannesburg. The mine started operations in 1902, and it operated as a glory hole. It wasn't benching or anything like that. It was just a big hole that they excavated down to a depth of 189 meters. And that went on until 1932. In 1932, really because of the depression in the world, they stopped mining, and they came back to in 1945, pumped it out, started looking at going underground, and they started mining again using open stoping mining methods in that pit, but accessing it via a shaft system. And they changed from, in addition to the open stoping, they also started doing block caving in 1972, because the other De Beers mines at that stage were also doing block caving. So they used that as the mining method with the extraction level down on the 385 meter level. And we went on from there to try and, as we went deeper, we tried open stoping as a mining method. That didn't work. We reverted back to block caving, and we went into the situation that we knew that we couldn't use the mining method, the scraper mining method that we used above the soil. So we went to mechanized caving. We had Dennis Loebscher as a consultant with us, and we went across to the Codelco mines. We looked at what El Teniente was doing, what Salvador and Dina were doing, and what Henderson were doing. And we designed our first block cave at depth on that basis. And that block cave operated for a long time, and they are still doing some block caving at Kalinin mine. The mine, obviously, as I said, has a long history, and they've mined over 450 million tons over the space of 104 years. And the diamonds that have come out of that pipe were in excess of 17 billion US dollars. And they've still got reserves for about another 30 years. They are currently using block caving and sublevel caving as a mining method. This again is just a diagrammatic of what the mine looks like. So it's a kimberlite pipe. It was intruded 1.6 billion years ago, and it's relatively big for a kimberlite pipe. Across the long axis, it's around 900 meters at surface, and on the short axis, it was about 400. So it was about 36 hectares in size. If you look across to the right-hand side, that's what the pipe looks like today, or what the mine looks like today. You can see it wasn't benched in the conventional way that they do these days. It was simply taken down, and you can see the old tunnels. These tunnels there are about 375 meters below surface, and the bottom of the pit these days is very close to 500 meters, and mining is going on below that. So the first mechanized cave that we put in, we called the BA5. It had an extraction level on the 630 meter level. It's that red block that I've just brought up, and that's where we ended up with some of the problems that I'm going to describe now. So this is just a diagrammatic 3-dimensional picture of what the ore body looks like, the Kalinin mine kimberlite ore body. It was intruded in 4 main phases. The first phase was this very weak kimberlite, which we call the brown kimberlite. And then the grey kimberlite, it's also quite weak rock, and then a lot more competent rock. So there were 4 phases of intrusion here. And one of the problems that you encounter with kimberlite is that it comes from quite a depth. It comes from at least 160 kilometers below surface, and then explodes to surface as a volcanic pipe. And a lot of the minerals, especially the olivine, just break down very quickly to clay. So there's a lot of clay in what I've labeled here, the very weak and the weak kimberlites. And when that's exposed to the air and especially to water, it can break down very quickly. A rock that has a competence of sort of 80 MPa can easily turn into a rock with almost zero competence if you allow the water to get in. And we've got pretty good definition of the pipe down to 1,100 meters. And this is what Kalinin mine is currently mining. This is just coming back to block caving. I think all block caves in one way or the other have this sort of layout. You have an extraction level, your production level, and then anything from 15 to 17 meters above that, you have the undercut level, and then you have the drawbells, which allow you to access the ore that gets generated up there from the extraction level. This is where your LHDs run, and you need to undercut your whole mining block. So you have undercut rings in some form or the other up there. And on the right-hand side, that little insert there just shows you that generally as you undercut, you create quite a high stress. And that's the stress that can do a lot of damage. This is just looking at typically what happens on that extraction level. If you take out only the light green tunnels, the main production tunnels, that means 13% of the ore on that level is taken out. If you then take out these draw point crosscuts, that's another 9%. And if you take out the drawbell areas, it gets to about 30%. So that's before anything happens, you can be in the situation that you've taken out 30% of the rock on the level below the undercut, which is often where the problems start. So above the sill, and in most of the other mines in the kimberlites, we used a post-undercut mining sequence. And the consequence of that was that the extraction level infrastructure was damaged by mining stresses. This is just a diagrammatic illustrating what we think happened. So you develop the undercut and the extraction level, and then you put in your drawbells. And once that's in, you start doing your undercutting. Go across it. So all the infrastructure on the extraction level is already developed before you do any of your undercutting. So those are the undercut rings that you bring in, and then you start loading, and when you do that, obviously the ore body starts to cave. But the problem that we had with this particular sequence was that because a lot of the development on the extraction level had already been done, it was subjected to some high stresses. And these photographs that you see here are the consequence of those stresses on the extraction level, the developed extraction level. So we had the production tunnels and the drawbells on the left-hand side. You can see the sort of damage. There was a lot of support put in, but that was damaged. On the right-hand side over here, you can see damage to a draw point down on the 630-meter levels. We simply couldn't operate. So what we did was we had to go back into those areas, and some of the infrastructure could be rehabilitated, but this was obviously expensive and time-consuming. And in some areas, the infrastructure simply couldn't be repaired, and we had to be recovered from the lower levels. In that particular mining block, we actually lost 2 extraction tunnels totally, and we only got the reserves associated with that on the recovery level. We also lost 40 draw points associated with those extraction levels, as well as in some of the contact areas. So there's a lot of support that we had to put in. So as a consequence of the problems that we had, we decided that we would change to an advanced undercut mining sequence where we only put in the amount of development that we thought we needed on the extraction level, before doing undercutting. Again, this is just diagrammatic. So you first do your undercutting, and only once the undercutting has been done, you put the drawbells in. So they are effectively in a stress shadow, and you don't have those high damaging stresses. And we also improved our support standards. So as there were tunnels that we couldn't operate in, we improved our support standard, and we put in better support. And you can see there that on the top left, that's the support that we installed across a contact zone. The bottom, that was typically what a production tunnel would look like after you'd supported it. And on the right, the big photograph is a draw point construction under there. And because the advanced undercut mining sequence worked well, we started to use it in a lot of the other blocks. So we had 3 additional blocks where we put in the advanced undercut mining method, and that was pretty successful. Not always, but relatively successful. So we mined this area pretty much out from 1986 down to 2010. Mining continued in this as well as in these areas. And then obviously we had to go deeper. And in 2008, started planning and implementing a new cave at a depth of, well, the undercut level was 824 meters below surface. And this is just a plan view of what that looked like, showing some of the geotechnical zones. You can see that the light brown on the undercut level, the mining rock mass rating was less than 40. The yellow, which made up most of the ore, mining rock mass rating was in excess of 40, and this was relatively competent with the mining rock mass rating at 50. This area over here, you can see that HR, that's where we initiated the cave. And this is just some more detail of that. So again, this is what the undercut level looked like. The green area at the bottom is where we started, and it's where we started and where we got the cave to initiate. So that was big enough for the hydraulic radius. And all of the infrastructure in the kimberlite was around there. So the tips are the passes, and we accessed that. And you can see we put the slot tunnels in using blind hole bores and retreated across that. So you can see the undercut face shape. We try to keep that shape, and we're pretty good at doing that. On the right-hand side, you can see it's in more detail. It's just a screenshot from mine 24D. So that grey area at the bottom, when we reached that, caving started, and then we went across the cave. And you can see it took us 4 years to get right across to the other side. We only did 4 rings a month, so it took us those 4 years to get across there. And Kalinin has been using geotechnical modeling for a long time, probably going right back to 1986. So the models are calibrated, the geotechnical models are well calibrated, and people have a pretty good idea, the mining people have a pretty good idea what it means when they look at the results of the geotechnical modeling. And you can see this particular model was done by David Beck, and it shows diagrammatically what the stresses were going to look like as we implemented this undercut and extraction level. You can see there's some areas where you're seeing red, and it's surrounded with a yellow surround, and call those fringe issues. That's the area of contact between the competent sidewall and the often weak and damaged kimberlite. So we expected problems there. And in the top right-hand side, we also expected some problems from monitoring, and we did what we could to avoid that. We increased our draw point spacing from 18 right up to 21 meters, and we also looked hard at what we could see on the ground in the tunnels, and we improved our support design accordingly. And this is the support that we put in on the extraction level, down on the 840 extraction level. You can see on the top left hand, that's typically maybe 20 meters, 30 meters of contact support across that area with massive support. And the one below it is what it looks like when it's finished. It looks good. On the top right hand is a production tunnel while they're still busy supporting. As I mentioned earlier on, one of the problems that you have with kimberlite is that when it's exposed to water, just to the atmosphere, it can deteriorate quite dramatically, quite quickly. So that blue that you see there is sealant. We have to spray sealant onto the sidewalls to stop that deterioration. And this particular mining block down on the 840 level has actually given us far less problems than when we first attempted to go to mechanized caving on the 630 meter level. So the labor force, everybody has learned a lot. We've learned from other people in the world. We've done a lot of changes, and this mining block is performing very well. The next mine that I'm going to talk about is Finch Diamond Mine, also situated in South Africa, about 200 kilometers away from the Kimberley area. On the right-hand side, you can again see you've got very competent dolomite wall rock, so that stood up very well. This infrastructure that you see down there is associated with open stoping down on about the 450 meter level. So that's just a big open hole there. The mine started as an open pit in 1963, continued as an open pit till 1991, and then they took out the remnants of what was left behind by the open pit with a modified open benching, and then they put in a block cave, and the mine was subsequently sold to Petra Diamonds, and they are now using sublevel caving as a mining method. And the sublevel caving mining method was chosen largely on the basis of timing. There wasn't time to put in the block cave, so they were happy with the block cave mining method, but unfortunately that there wasn't enough time to implement everything that we needed to implement. So this again is just a diagrammatic of the Finch mine. You can see there's 3 blocks were mined out, and the block that I'm going to talk about is this high-colored block here. Block 5 is where they were mining subsequently to that. So this is the block that I'm talking about now. The mine layout was very much the same as what we'd found worked at Kalinin. So we had an extraction level. It was an offset herringbone extraction level. The blue is the level at the bottom. The yellow is the undercut level. And the blue is the rings that we opened up. Pretty much the same thing, just with a bit of an isometric view. Unfortunately, what happened was that we started getting bad damage to tunnels even before any mining had started. And it became untenable in some areas, so something else had to be done. And two of the two geotechnical people that were mainly responsible for this was David Wilson and Sammy Tamil. I think both of them have been involved with Oyo Tolgoy for some time now. They have been there. So what happens was in 1998, on the basis of core drilling, they came up with a rock mass rating of, you can see there, 40, 45, 50. With time, and you adjust that using Dennis Lapsher's mining rock mass rating, and the average mining rock mass rating that we were looking at in 98 was about 35. When they re-evaluated those tunnels, did some additional drilling, they found that the mining rock mass rating, the rock had deteriorated just because it was exposed. And when they went back and did additional work in 2002, it was even worse. So where we thought we'd be dealing with that sort of rock mass rating, it actually deteriorated just as a function of opening up those tunnels and no mining at all. This is just a plan view of the undercut level at Finch Mine, and they did a lot of detailed mapping of that area. And based on that mapping, they came up with different support designs. So you can see on the right-hand side, a lot of the rock mass rating was not good in those areas, and they took heed of that, and they designed the support according to what the rock mass ratings were. So you can see in this contact area, that grey area, that was always quite damaged by the interface where water had moved through, and they needed special support in those areas across all the tunnels. Where there was intersections of tunnels at the center of the pipe, there was quite big spans, so again they had to put in additional support there, and there were some areas generally associated with some dikes where there was also additional support. And typically this is what it looked like. So the support standards were improved markedly. The support standards mainly coming across from Kalinin were just not adequate for Finch. So they had to put a lot more into that. So you can see what the revised support standards looked like and what the production tunnel looked like. And those tunnels stood up very well for the whole life of that block. So they mined there for the better part of 10 years. And there was very little rehabilitation required once they'd done the geotechnical mapping, done the correct support for those areas. This graph, I think Ferran's already showed you pretty much the same graph, but updated. And it just goes to emphasize that block caving has really evolved as a mining method over the last 20 odd years. And you're starting to get some of these massive caves coming in at depth, generally in excess of 1,000 meters, with very high production rates. And Oyu Tolgoi is certainly in line to go down that route. These are just estimates of what the tonnages are that are being produced or will be produced in these mining areas. And these are just my own comments around block caving, my thoughts and what I've learned over the years. This method was developed more than 100 years ago, and it's evolved remarkably during the last 20 years. It's a very safe mining method. If you neglect some of the big coal mines, block caving is the largest and lowest cost underground mining operation, and successful block caves need experienced, educated personnel. I think every ore body is unique, and mine personnel can increase the rate at which they're gaining experience by analyzing and understanding all the data that becomes available as mining progresses, and they can start calibrating those stress models that gets done, and they can certainly accelerate the rate at which they learn. And the mine personnel become the experts in using the cave mining method on their mines, because every single ore body is unique. So you've got to learn as the personnel on the mine, and that certainly works on all the mines that I've seen. And I think the Mongolian University of Science and Technology can certainly play an important role here. Well, they can look at that data, they can assist where they can, and they can probably supply MSc and PhD students so that you really get to know what your ore body is about and start to use that information to improve your operation. The second point is you need a detailed knowledge of the ore body and surrounds if you're going to be effective as a block caving operation. You need the discipline as an operation to stick to your long-term plans. You can't increase and decrease the mining rates quickly and think that nothing's going to happen. It will have consequences. The major drivers of block cave development have been shared experiences across the world. Everybody talks to everybody else. Everybody knows what everybody else is doing. It's very free and easy. There have been good improvements in technology, all sorts of technology, and this has allowed improved production planning and draw control, and there's also computer-aided mine design. And what these big block caves do is they provide an income stream for government. They create jobs, and they lead to infrastructure and skills development over a long period of time. And as I said, with Kalinin, it's been going for more than 100 years. And Chip was talking yesterday about Henderson, that was 45 years of development. Finch, again, 40, 50 years of development. Alteniente, hundreds of years of development. And I think the other thing that is worthwhile thinking about, there are always problems that get encountered, but all of those have been solved. And as far as I know, no major block cave mine has closed in the last 20 years because of technical problems. And block caving will undoubtedly continue to develop as a mining method. Thank you.
Thank you, sir. Thank you very much for your presentation. As you said, no major block cave mines closed in the last 20 years because of technical problems. So it is a complex mining operation, but we are learning a lot and solving lots of problems. So Patrick, we will have Q&A discussion after almost 3 hours. So let's meet again at that time.
Good. Thank you.
За ингээд дараагийнхан илтгэл рүү орё. За манай дараагийн илтгэл блокоор нураах.
Let us proceed to the next presenter.
Туршлагаас үргэлжлүүлэн хуваалцсан.
Underground block caving experience will be shared with us as well. Kodelka, Chile and Kodelka asset, LTNT mine experience will be shared with us.
Танилцуулгыг хийх илтгэгч маань Гэвэн Фергюсон
Mr. Ferguson is our speaker.
Болоорын төслүүд дээр болон санхүү тал дээр 40 гаруй жил ажилласны туршлагатай.
The operational experience, financial experience, the long experience, the hands-on involvement in block caving project, in the planning, operations, validation, the also accreditation in all the risk assessment in all different aspects that was involved in Kodelka Newcrest experience.